So now let's do the calculus. In the main video, we reached this point and then magically got to the answer. So again, the electric field, bunch of constants, integral from one end of the line to the other end of the line over this expression. Now, the first thing that's interesting thing about this is that if we integrate symmetrically, like we do here, instead of integrating from the left end to the right end, we could integrate just from the middle to one end and double the result. So that's the first thing we're going to do to make this simpler. So we're going to double the answer and change our limit of integration. Zeros are always nice algebraically. Well, they're often nice algebraically. And now, for those of you who are in calculus, you're going to learn many techniques of integration. One of the techniques of integration is substitution, and specifically trig substitution. One of the reasons you might think to use a trig substitution is because we have an x squared plus y squared here, and that looks like part of the Pythagorean theorem. So we are going to make a triangle. And through extra knowledge, because you can substitute with sine, with cosine, with tangent, with cotangent, with cosecant, you can do a lot of different trig functions for different cases. But for this specific one, we are going to substitute that x is equal to y times the tangent of u. And u is a new variable. It's one I'm making up. So if you want to think of it as u substitution, you can. But I'm specifically going to substitute that x is equal to y times the tangent of u. Now if we go back to a regular triangle with x and y, we know this is r, same r from before, and this is theta, back from our original triangle. U is up here, and I know u is up here because the tangent of u would be x over y, opposite over adjacent, x is opposite, y is adjacent. So that's our triangle, and we're going to come back to that later. We also need to substitute for dx. If we're going to get rid of x completely, we've got to substitute for dx. So I need to take the derivative of this substitution expression. So dx equals y. Well, y, remember, is a constant. That's why we were able to pull it out over here, so it doesn't get it included. And then the derivative of tangent is secant squared u. And I don't think I'm not sure if y'all have gotten there or not in calculus, but when you get there, if you haven't already, you'll know that the derivative of tangent is secant squared. And then, because we have our new variable, we need to include its differential. So dx turns into something times du. So now I'm going to simplify, but instead of doing the whole thing, I'm just going to look at the inside. So if I rewrite the inside, dx over x squared plus y squared to the 3/2 power equals, my numerator is this, y secant squared u du, and my denominator is x squared, so I need to square this, y squared times the tangent of u, tangent squared of u, plus y squared, all times, or all raised to the 3/2 power. Now I can simplify this by pulling out the y squared. So y secant squared u du over, now I will use the brackets, y squared times tangent squared of u plus 1, all to the 3/2 power. And the reason for doing that is we have a trig identity here. Tangent squared plus 1 is equal to secant squared. So y secant squared u du over y squared secant squared u to the 3/2 power. Now we can distribute this 3/2. So, and we still haven't done anything to the numerator. Secant squared u du over our denominator, y squared to the 3/2 power is y cubed. Secant squared to the 3/2 power is secant cubed. And now you see why we did this. Look at how much cancellation we're going to get. So the y and the y cubed, we're just left with y squared. Secant squared and secant cubed, we're left with secant of u, and our numerator is only du. And last one, remember that secant is 1 over cosine. And so since we have a 1 over something in the denominator, I would rather write this as the cosine of u du over y squared. So we now have a much, much easier integral to perform. We have all these constants times the integral from 0 to L over 2 in the x variable. With this thing, now turns the inside turned into integrating over cosine. Much, much easier. So let's turn the page and rewrite it. So our E equation, all those constants, 2k lambda y, integral from x equals 0 to x equals L over 2. And then our inside is the cosine u du over y squared. So let's already make things simpler. Notice that we have a y squared. Well, that's a constant. Y is the distance from the center of the line to that point at the top. So 2k lambda over y, because y and y squared, one of them cancels. Integral of x equals 0 to x equals L over 2 of cosine u du. And again, don't remember if you know the trig functions yet in calculus, but the integral of cosine is just sine. So 2k lambda over y, sine of u, evaluated from x equals 0 to x equals L over 2. So we do have this issue. We've got to get rid of u. And remember that u came from, let's flip back. We could rearrange this with x and y, but that gets rather complicated. The other thing we can do is look at this triangle. What we need is the sine of u. We don't actually care about u. We care about the sine of u. And if we look where u is in this triangle, sine is opposite over hypotenuse, x over r. So this is 2k lambda over y, x over r, which is the square root of x squared plus y squared. And we need to evaluate that between x equals 0 and x equals L over 2. So I'm going to keep all of my constants out front as I do my evaluation. So 2k lambda over y, big ol' bracket, substitute an x both places with L over 2, subtract substituting in 0 from both places. So L over 2 over the square root of L over 2 squared plus y squared minus 0 over the square root of 0 squared plus y squared. Well, our denominator is just y here, but 0 divided by anything is just 0, so that term disappears. And we have 2k lambda over y times L over 2 square root of L over 2 squared plus y squared. And I'm going to stop there because the main video, this was the next line. And from here in the main video, we evaluated if y is really big, we get a point charge. If L is really big, we get an infinite line. So, hope you enjoyed it.